shortest path in a directed acyclic graph. Given a directed acyclic graph of v vertices from 0 to n minus 1 and 2D integer array, uh, ranges of length e, where there is a direct edge from this is the distance of, okay, find the shortest path from source vertex to all the vertices, and if it's possible, if it's impossible to reach a vertex, then return -1 for the vertex. Okay. So what we have here is we have a vector of edges, right? Instead of taking this, let us take this, right? And what we are given is this. 5, 3.1. Yeah. So this is what they gave. And how are we gonna interpret this data is that they said we have an edge from edges 0 to edges 1 with cost of edges 3. That's what they gave. Sorry, edges 2. So, yeah. So now let us draw a graph based on that. 0 to 1, we have an edge with cost 2. 0 to 4, we have an edge with cost 1. 4 to 5, we have an edge of cost 4. 4 to 2, I have an edge with cost 2. 1 to 2, we have an edge with cost 3. 2 to 3, we have an edge of cost 6. And 5 to 3, we have an edge of cost 1. So this is the graph. And now we are supposed to find shortest distance from SR's source to other nodes. And this can be achieved by the Dijkstra algorithm. Plus BFS. The Dijkstra algorithm says that if we have a distance u or distance from source to the node plus v cost of to the parent node, cost of the edge between parent node and child node is less than distance to that v to that node, the child node to be precise. Then we're gonna update the distance of the child node with the new path which we got from the parent node u, right? So to achieve this, let us have uh, an area of distance for all the nodes. So that is for 0, 1, 2, 3, 4, 5 to infinity. Because we didn't visit any of these nodes, so we don't know the distance. So since we didn't reach any of the nodes, so we are assuming that the distance to all the nodes is infinite at present. Right. Now, what did they give? They gave that the source node is gonna be 0. So this is our source. Now, what we're gonna do is we're gonna take a queue for BFS traversal, and what we're gonna push is we are gonna push the node and the cost, right? So for our source node, the node is 0 and the cost is gonna be 0 because we don't have a path from 0. We don't have an incoming edge to 0, so the cost is gonna be 0. So we're gonna push 0 comma 0 inside, and then we are gonna see its neighbors, that is 4 and 1. Since u plus v, that is 0 plus 0, is less than infinity, we are gonna update the distance of 0. Why do we have u as 0? Because it is our source node and we don't have an incoming edge. So that's why v is 0. And distance from source to source is 0. So we have 0 plus 0 is equal to 0, which is less than infinity. Now we are gonna pop this out and push its neighbors, that is 1 comma 2 and 4 comma 1. Right. So now we have the parent node of 1 is 0 and the distance of the parent at 0 is 0. So 0 plus cost of the edge is 2, which is 2 less than infinity. So we're gonna update this to 2. And then we're gonna pop it out. While popping it out the 1, we are gonna push its neighboring edge, which is 2 comma 3. Right. Now here, distance of the parent node, which is 0, is gonna be 0. That implies 0 plus the cost is 1, which is 1, and that's less than infinity. So we're gonna update. Oh, sorry. We're gonna update this one, and we're gonna pop this out. So before popping out, we're gonna enter its neighboring nodes. That is node 5 with cost 4, node 2 with cost 2. Right. So now here the parent node of 2, parent node of 2 is 1, because here we got it via node 1, via node 4. Right. Distance of node 1 is gonna be 2. So 2 plus 3 is gonna be 5 less than infinity. So we're gonna update this distance to 5, and we're gonna pop it out. So while popping it out, we are gonna insert 3 comma 6. You know what? I'm gonna write this somewhere above. Okay. Node cost. Right. So now for node 5, mm, the distance from the parent node, distance till the parent node is gonna be 1. So 1 plus the cost of edge is 4, resulting to 5, which is less than infinity. So we're gonna update it to 5, and we are going to pop it. So while popping it, we're gonna push 3 comma 1 into the key. Right. Now distance 4 is 1 as discussed earlier. So 1 plus 2 is 3 less than 5. So we are gonna update the distance, and we are gonna pop this out. 2 comma 6. So distance of 2 is the updated value is 3. So 3 plus 6 is gonna be 9, which is less than infinite. So we're gonna change this to 9 and we're gonna pop. Here, the distance till the parent node, which is 5, is 5. That implies 5 plus 1 is gonna be 6, which is less than 9. So we are gonna update the value of 3 to 6. So our final answer is gonna be 0, comma 2, comma 3, comma 6, comma 1, comma 5, which is pretty much what we got here. So let us pull this up. Okay. So first we are gonna initialize distance vector, which is gonna be of size of the number of nodes, and it's gonna be initialized to I infinity. And let us define infinity, which is gonna be int max. Right. Now what we're gonna do is we're gonna initialize q and we're gonna push. Let us keep it as it would be better this way. So we're gonna push 0.0. So why q is not empty? Hmm, not then no, it's gonna be this, or let's give this cost. Cost is gonna be just of let it just be child cost is relatively second if instance of parent node plus cost is less than distance of child node, then q dot push child node comma child cost. Okay, this is pretty much what we this is pretty much our BFS plus Dijkstra. Um, replace INF with -1 for unreachable edges. For an I is equal to 0, I is less than I plus twice. If the sum of I is gonna be -1, we are gonna return cheese. Mm, or wait, let us keep it as Wait. Accessing it like this is little difficult. So what we're gonna do is let us create an adjacency list. It should be way better than this. So let us create an adjacency list. We should V so up here is gonna be coming value. Distance of zero is gonna be zero. Mm, So this is the final code for the problem. Here we made our adjacency list for better traversal and accessing than that of H. And here we stored node and distance of the node, right?